Linear algebra. It's a secret code that reveals the underlying structure of so much of what we see and build. From the way light bounces to how your search engine finds information, linear algebra is there, working silently in the background. It's a tool for understanding, a lens to view the cosmos of data and dimensions that surrounds us every single day. Think of it as a fundamental force like gravity, but for organizing information and solving complex problems. This journey we're about to embark on will take us through its core ideas. We won't get bogged down in terrifying equations that stretch for miles. Instead, we'll explore the concepts, the why, and the what for. Imagine you're learning the rules of a grand cosmic game. The pieces are vectors, the playing field is a vector space, and the moves are transformations. Linear algebra gives us the rulebook. It helps us predict outcomes, find the best strategies, and even uncover hidden patterns that were invisible before. It's about seeing the simple elegance that governs complex systems, a theme that resonates throughout the entire universe. We use linear algebra to describe relationships between many things at once. Your smartphone uses it to rotate your screen. Movie studios use it to create breathtaking special effects, moving and morphing characters in three-dimensional space. Economists use it to model complex markets with countless interacting agents. So, where does our journey into linear algebra truly begin? It starts with something called a vector. You might picture an arrow, and that's a great start. An arrow has a length or magnitude, and it points in a specific direction. Think of the force of gravity pulling you down. That's a vector. Or the velocity of a spaceship hurtling towards Mars. That's another vector. These arrows can represent so many different things: forces, speeds, even a list of ingredients for a cosmic cake. They are the fundamental building blocks, the atoms of linear algebra. We can add them together, stretch them, shrink them, and they live in a special kind of playground. This playground is what mathematicians call a vector space. It's not a physical space like your living room, though it can be. It's a collection of all possible vectors of a certain type, along with a set of rules for how they interact. For example, the familiar three-dimensional space we live in, where every point can be described by three coordinates, like length, width, and height, is a vector space. Now that we've explored vector spaces, let's zoom in. Imagine a flat, infinite tabletop within our three-dimensional universe. Any vector on this tabletop can be added to another, and it stays on the surface. Stretch or shrink a vector, it remains on the tabletop. This tabletop is a subspace, a smaller vector space within a larger one. Subspaces simplify problems by focusing on relevant dimensions. Imagine standing in the sun. Your body casts a shadow on the ground. That shadow is a projection of your three-dimensional self onto the two-dimensional surface of the ground. In linear algebra, we have a mathematical tool that does something very similar, the projection matrix. A projection matrix takes a vector in a high-dimensional space and finds its shadow or its closest representation in a lower-dimensional subspace. It's like simplifying information, keeping only the most relevant parts that fit within a certain constrained world. Why would we want to cast these mathematical shadows? Well, often, real-world data is messy and doesn't perfectly fit our ideal models or subspaces. A projection matrix helps us find the best possible approximation. For example, if you have a bunch of data points that almost lie on a straight line but not quite, a projection can help you find the line that best fits those points. This is the core idea behind techniques like least squares regression, which is used everywhere, from fitting trend lines in economic data to training machine learning models. Section 5. Quadratic forms, sculpting with equations. Let's venture into the world of shapes and energy, described by a special kind of mathematical expression called a quadratic form. You've likely met quadratic equations before, like y equals x squared, which draws a simple parabola. A quadratic form is like a higher dimensional version of this. Instead of just one variable x, it involves multiple variables, all raised to the power of 2, or products of two variables. Think of expressions like x squared plus y squared, which defines a circle or a cylinder's base, or more complex ones like a x squared plus by squared plus cz squared plus dxy plus exz plus fyz. These forms sculpt surfaces in multidimensional spaces. These mathematical sculptures are not just pretty, they are incredibly useful. In physics, the kinetic energy of a rotating object can be expressed as a quadratic form involving its angular velocities and moments of inertia. In economics, utility functions or cost functions can sometimes take this shape, helping to find optimal points. Section 6. Orthogonal matrices, the guardians of geometry. Imagine a perfectly crafted crystal. You want to rotate or reflect it without distortion. Orthogonal matrices perform these transformations. They preserve lengths and angles. Guardians of geometry in linear algebra. What makes a matrix orthogonal? Its columns are orthonormal vectors. Each column vector has a length of 1 and is perpendicular to others, like the x, y, and z axes in 3D space. An orthogonal matrix defines new perfect axes. Multiplying a vector by an orthogonal matrix re-expresses it. Its transpose is also its inverse. Section 7. Eigenvalues and eigenvectors. The universe's fingerprints. Imagine you have a spinning top. As it spins, most points on the top are moving in complex circles. But there's one line of points, right through the center, along the axis of rotation, that isn't changing its direction. Points on this axis might move up or down along it, or stay still, but the direction of the axis itself remains fixed. This special direction is like an eigenvector, and the amount by which points on it stretch or shrink, or if they stay put, is related to its eigenvalue. These concepts are some of the most powerful and revealing in all of linear algebra. When a matrix acts on a vector, it usually transforms it into a new vector pointing in a different direction and having a different length. However, for any given square matrix, there are certain special vectors, the eigenvectors, that when multiplied by the matrix don't change their original direction. They only get scaled, stretched, shrunk, or perhaps flipped to point the opposite way. The factor by which they are scaled is the eigenvalue associated with that eigenvector. It's like the matrix has a preferred set of directions where its action is very simple, just a scaling. Section 8. LU Decomposition, solving systems with finesse. Imagine you have a complicated puzzle, like a Rubik's Cube. Solving it directly can be tough, but what if you could break down the scrambling process into a sequence of simpler known moves? LU decomposition does something similar for matrices. It's a method to factorize a square matrix A into the product of two simpler matrices, a lower triangular matrix L and an upper triangular matrix U. So A equals LU. A lower triangular matrix has all zeros above its main diagonal, and an upper triangular matrix has all zeros below its main diagonal. This factorization makes solving certain problems much easier. Why is this A equals LU breakdown so useful? Its main application is in solving systems of linear equations, which look like x equals b, where A is our matrix of coefficients, x is the vector of unknowns we want to find, and b is a vector of constants. If we can write A as LU, then our equation becomes LUX equals b. We can then solve this in two much simpler steps. First, we solve I equals b for y. This is easy because L is lower triangular, using a process called forward substitution. Section 9. Singular Value Decomposition, SVD, the ultimate data unveiler and concluding thoughts. We've journeyed through vector spaces, shadows, rotations, and special directions. Now, we arrive at what many consider one of the crown jewels of linear algebra, singular value decomposition, or SVD. If linear algebra were a superhero team, SVD would be its most versatile and powerful member. It's a factorization of any matrix A, not just square ones, into the product of three other special matrices. A equals UV3. Here, U and V are orthogonal matrices, remember them? They handle rotations and reflections. And C, sigma, is a diagonal matrix containing special values called singular values. What makes SVD so incredibly powerful is its ability to break down a matrix into its most fundamental components and reveal the geometry of the transformation it represents. The columns of U are called the left singular vectors, the columns of V are the right singular vectors, and the diagonal entries of C are the singular values. These singular values are always non-negative and are usually arranged in decreasing order. They tell you how much stretch or importance is associated with each corresponding pair of singular vectors. It's like finding the most significant actions a matrix can perform on vectors. The applications of SVD are vast